Hello friends, welcome to lecture series on matrix analysis with applications. So, today we will discuss about vector spaces, that what vector spaces are. So, let us start. Now, vector spaces V over a field F consist of a set on which two operations called addition, which is denoted by plus sign, and scalar multiplication, which is denoted by a dot, respectively are defined such that the following axioms are satisfied. So, what are axioms? The first axiom is you take any uv in V, then u plus v also belongs to V. That means this addition is a binary operation. That means this satisfies closure property. You take any arbitrary u and v in V, then the with respect to addition the sum is also in V. Okay. Now, for all x y z in V, x plus y plus z and then is equal to x plus y plus z, if you put the brackets in the first two or in the last two, both are same. So, that is associative property with respect to addition. Next property is there exists an element V, there exists an element in V denoted by 0. This 0 is not usual 0, this is simply a notation, and this denote identity element with respect to addition, such that V plus 0 equal to 0 plus V equal to V for every V in V. Okay. Then for every u in V there exists V in V such that u plus V is 0, and this V is called inverse of u with respect to addition. And the next is for every u V in V, u plus V is equals to V plus u, that is commutativity of addition. So, these 5 properties are with respect to addition, and we can also say that vector space V with respect to plus must be an abelian group. Okay. Now, with respect to dot, for each alpha belongs to field, V belongs to V, alpha dot V also belongs to V. Okay. So, that means dot is a binary operation, that means, but this binary operation is defined one is from field, other is from vector space. Now, for each V in V, one dot V also belongs to V. The next is for every alpha belongs to field, u V belongs to V, alpha dot u plus V is equal to alpha dot u plus alpha dot V, and for every alpha beta belongs to field, u belongs to V, alpha plus beta dot u is equal to this. So, if a vector space V over the field F with respect to addition and scalar multiplication dot satisfy these 9 properties, then we say that is a vector space over the field F. Now, the elements of the field F are called scalars, and the elements of the vector space V are called vectors. Now, these vectors are not the usual vectors which we study in physics. We simply call the elements of vector spaces as vectors, that is all. Okay. So, what is a vector space? We satisfy this property, that means if we are talking about a set V over the field F, we sometimes write it like this. Okay. Now, with respect to plus, it must be an abelian group, and with respect to dot, this V must satisfy the following properties, which are for every alpha belongs to field, V belongs to V, alpha dot V must belongs to V, 1 dot V must belongs to V for every V belongs to V, then alpha plus beta dot V must be equal to alpha dot V plus beta dot V for all alpha beta from field and V belongs to V, and alpha dot u plus V must be equals to alpha dot u plus alpha dot V for all alpha belongs to field and uv belongs to v. So, with respect to addition, this V must be an abelian group, and with respect to dot, V must satisfy these properties. Then we say that V over F is a vector space. So, now let us discuss few examples based on this. Now, you take V as R2, a simple example V as R2, and say field is R. What is R2? R2 is simply R2 means all x comma y such that x and y both are in R. Now, the next is how addition and scalar multiplication is defined. Then only it will constitute a vector space over that addition and scalar multiplication. So, addition is defined as you take any two elements in R2 and this is simply A1 plus B1, sorry, A1 plus B1, you can simply write here B1, A1 plus B1, and this is A2 plus B2. This is about addition. Now, the scalar multiplication is alpha dot A1 A2 is alpha A1 and alpha A2. If we defined these operations, this plus, okay, this plus which is defined like this. Now, this is one vector in R2, this second vector in R2. This is the operation addition which is defined on the two elements of the vector spaces. This addition is usual addition, the addition of two real numbers, okay, and this is a dot which is operated on a element of field and element of a vector space. And how it is defined? This is simply alpha A1, alpha A2. Now, first you have to see that V over plus must be an abelian group if it is a vector space. So, the first element is this plus must be a binary operation, or we can say that with respect to plus it must be closed, closure property must be satisfied. So, this is very clear that if you take this element is in R2, okay, you take let u and v belongs to R2 or V, then u will be equal to some A1 A2 and v will be equal to some B1 B2. Now, if you take u plus v which is A1 A2 plus B1 B2, it is equal to A1 plus B1 by this definition and A2 plus B2 which also belongs to R2. That means what? That means it satisfies closure property. Okay. The second property is associative. If you take the associative property, it is very obvious that if you take three elements A1 A2 and B1 B2 C1 C2 in R2, you take the bracket in the first two, you add them. So, you can by simple calculation you can easily show that this is equal to A1 A2 plus B1 B2 plus C1 C2. That means whether you take the bracket in the first two elements or you take the bracket in the next two elements, last two elements, both are same. It is very easy to show. You can simply proceed using this addition operation. The third property is commutative. The commutative is very simple. If you take A1 A2 and plus B1 B2, any two elements of R2, if you add them by this addition operation, you can see that is equal to A1 plus B1, A2 plus B2, which can be written as B1 plus A1, because real numbers are always commutative. 2 plus 3 same as 3 plus 2, and it is equals to and it is B2 plus A2. So, again by this definition we can write it B1 B2 plus A1 A2. So, we can say that u plus v is same as v plus u for all uv belongs to v. So, that means commutative property is satisfied. Now, if you talk about the existence of identity element, then you can simply see that if you add 0 0 to any element, we will get itself. So, if you take any A1 A2, add 0 0, you will get A1 A2, and it is true for all A1 A2 in R2. That means we have shown the existence of identity element, and the inverse of any A1 A2 is minus A1 minus A2, which is again in R2. Inverse means if you add these two, so it is equal to 0 0. So, we have shown all the 5 property with respect to addition. That means it satisfy that way V with respect to plus is a abelian group. Now, with respect to dot, if you see the first property, you take alpha belongs to field, where field is real here, and you take any u which is given by A1 A2 in R2. If you take alpha dot A1 A2, then by the definition of scalar multiplication, we can easily write alpha A1 alpha A2, and it again belongs to R2. That means closure with respect to scalar multiplication is satisfied. Now, the next property is you take 1 dot V, that means 1 dot A1 A2, which is by the definition is again A1 A2, that is V. So, 1 dot V is equal to V for every V in V. That means the second property holds. Now, if you take alpha plus beta dot with V, so it is alpha plus beta dot V, V here is A1 A2. So, it is alpha plus beta A1 by the definition, alpha plus beta A2. So, it is equals to alpha A1 plus beta A1, it is alpha A2 plus beta A2, which is equals to alpha A1 alpha A2 plus beta A1 beta A2 by the definition of addition, and this is alpha dot A1 A2 plus beta dot A1 A2, which is equals to alpha dot V plus beta dot V, and it holds for every alpha beta in field, and V belongs to V. That means this property hold for every alpha beta in field, and V belongs to V. And the last property is alpha dot U plus V, alpha dot this is alpha dot U plus V must be equals to alpha dot U plus alpha dot V. So, to hold this property, to prove this property, alpha dot say U is A1 A2 and say V is B1 B2. So, this will be alpha dot, this is A1 plus B1 comma A2 plus B2, okay, by the definition of addition, and this is equals to by the scalar multiplication, this is alpha times A1 plus B1 and this is alpha times A2 plus B2. This is alpha A1 plus alpha B1, this is alpha A2 plus alpha B2, and that can be written as alpha A1 alpha A2 plus alpha B1 alpha B2, and this is equals to alpha times U alpha dot U plus alpha dot V, where U is A1 A2 and V is B1 B2, and this property holds for every alpha belongs to field and for every UV belongs to V. So, we have shown that all the 9 properties are satisfied. That means this that means this R2 over the field R under these operations of addition, scalar multiplication is a vector space. So, these are few examples of this. The first example we have discussed. So, say we are having instead of R2 we are having Rn. Okay. If we are having Rn over the field R, or we also read it like this, Rn over the field R, and how addition scalar multiplication is defined, you take any u which is in Rn, that is A1 A2 up to An, V is also in Rn, that is B1 B2 up to Bn, and the addition is defined as A1 plus B1, A2 plus B2, An plus Bn, that is component wise addition, and scalar multiplication is alpha dot u is alpha dot A1 A2 up to An is alpha A1 alpha A2 up to alpha An is a vector space. Now, second, this can be proved easily as we did for R2 over R. Okay. Now, second example is the set of all real polynomials of degree less than equal to n over a real field under usual addition and scalar multiplication of polynomials is also a vector space. You can see here. Now, you are considering V as Pn. Pn is all polynomials of degree less than equal to n and field is R, and addition is standard addition of two polynomials and scalar multiplication is standard multiplication of a scalar with a polynomial. So, how can it constitute a vector space? So, this is very easy to show. You can simply see that the first is V with respect to plus must be an abelian group. Okay. In order to show that V plus is an abelian group, the first property is closure, that means plus is a binary operation. So, that is simple to show, that you take a n x raised to power n plus a n minus 1 x raised to power n minus 1 and so on up to a naught. Okay. This is the first polynomial, that is u, and the V is suppose b n x raised to power n plus b n minus 1 x raised to power n minus 1 and so on up to b naught. Okay. So, these are two polynomials whose degree are less than equal to n. It may be less than n also if these are coefficients are non-zero, I mean 0. If it is 0, then degree will be less than n. Okay. So, we are not putting any restrictions on the leading coefficients. Now, if you take u plus v, then if you take component wise addition as defined, so this is something like this. Then this is again belongs to V, because it is also a polynomial of degree less than equal to n. That means closure with respect to addition is satisfied. The second property is associative. That is very easy to show. If you take u plus v plus w, or is also equals to u plus v plus w for every u v w belongs to V. That you can easily show. You take the left hand side and then solve it. You take the right hand side, or from the left hand side itself you can easily show the right hand side. You can arbitrarily choose u as one polynomial of this type, v as this polynomial of this type, and w as some c n x raised to power n, c n minus 1 x raised to power n minus 1 and so on. Next is commutative. Commutative is also easy to show. You take u plus v, which is a n, which we have already seen that it is a n plus b n x raised to power n plus a n minus 1 plus b n minus 1 x raised to power n minus 1 plus and so on a naught plus b naught, and this can be written as b n plus a n, because these are real numbers and real numbers commute with respect to addition. This is b n minus 1 plus a n minus 1 x raised to power n minus 1, and this is a naught b naught plus a naught, and this can be written as b n x raised to power n plus b n minus 1 x raised to power n minus 1 and so on b naught by the definition of addition, vector addition. This is a n x raised to power n plus a naught. So, this is v plus u for every u v belongs to v. So, we have shown that it commutes. Now identity element is 0 polynomial. 0 polynomial is an identity element. If you take u plus 0, it will be 0 plus u equal to u for every u in V. Okay. And the inverse of any u is minus u. You can simply say that if you take u plus v is equals to v plus u equal to 0. So, this implies v is minus u for every u belongs to V. So, for every u there exists a inverse which is additive inverse. It satisfies commutative property, associative closure. So, this means with respect to plus it is an abelian group. Now, with respect to multiplication also, if you see the multiplication, so first property is alpha dot u. If you take alpha dot with a naught x raised to power n plus a n minus or a n x raised to power n, a n minus 1 x raised to power n minus 1 and so on a naught, which is alpha a n x raised to power n plus alpha a n minus 1 x raised to power n minus 1 and so on up to alpha a naught, which also belongs to V, because it is again a polynomial of degree less than or equal to n. So, the first property with respect to scalar multiplication is satisfied, which is closure. The second is 1 dot u. If you take alpha as 1, so it is simply a n x raised to power n plus substitute 1 here in place of alpha. So, it is a n minus 1 x raised to power n minus 1 and so on a naught, which is equal to u for all u in V. So, next property also hold. Then you take alpha plus beta time dot u. So, it is alpha plus beta dot with u is a n x raised to power n plus and so on a naught. So, it is alpha plus beta times a n by the definition of scalar multiplication. Then it is a n minus 1 x raised to power n minus 1 and so on alpha plus beta times a naught. Okay. Now, it is alpha a n plus beta a n. Okay. Then they can be split into 2, alpha this alpha n minus 1 into x raised to power n minus 1 and so on alpha a naught plus with beta a n x raised to power n plus and so on beta a naught, and this can be written as alpha dot with a n x raised to power n and so on alpha and so on a naught plus beta dot with a n x raised to power n and so on a naught. So, it is alpha dot u plus beta dot u for all alpha beta belongs to field and u belongs to u. And similarly we can show the last property, that this is equals to alpha dot u plus alpha dot v for all alpha belongs to field and u v belongs to V. So, in this way we can say that it constitute a vector space over a real field. Okay. Now, next example is, if you consider set of all m cross n matrices, real matrices over a real field under usual addition of matrices and usual scalar multiplication of a scalar with a matrix, it is also a vector space. It is also very easy to show that with respect to plus matrix, the set of matrices is a vector space, is a abelian group, and with respect to dot is satisfy all those 4 properties. Okay. The next is, if you take the set of all real and continuous functions defined in the interval 0 1. Okay, you take the set of all continuous functions, real and continuous functions which are defined in between 0 and 1. Suppose it is denoted by C 0 1 over a real field with the addition defined like this and scalar multiplication defined like this, is also a vector space. You can simply see with respect to plus, the sum of 2 continuous functions is also continuous. So, closure is satisfied. Identity element is 0, 0 is a continuous function which belongs to this set. The inverse of any element f in 0 1, C 0 1 is minus f, which is also in C 0 1, that is inverse element exists, and f plus g is equals to f x plus g x, which is same as g x plus f x, that is g plus f, that is commutative property hold, and this also satisfies associativity. That means V with respect to plus is an abelian group. Now, if you see with respect to dot, also you can easily see that if you multiply a continuous function by a non-zero scalar, by any scalar in fact, it is also a continuous function. Then 1 dot f is equals to f, that is 1 dot v equal to v, and similarly the other two properties, that is alpha plus beta dot v equal to alpha dot v plus beta dot v, and the last property is alpha dot u plus v should be equals to alpha dot u plus beta dot v. So, in this way we can also show that this constitute a vector space over the field R. Now, these are the important theorem that in any vector space over any field f, if it is a vector space over the field f, then these three properties also hold, and it is very easy to prove. You can see here the first property is, and it is for any alpha, it is alpha for all alpha in field. Now, this 0 is from field, I mean this 0 is from vector space. This 0 is not a usual 0, it is a 0 of a vector space. So, this 0 is a additive identity basically, and we have to show that if you take a scalar multiplication of any alpha with this additive identity, it is always 0. So, the proof is easy, you take left hand side, it is alpha dot 0, which can be written as alpha dot 0 plus 0, which is equals to, because it is a vector space. So, alpha dot u plus v is equals to alpha dot u plus beta dot v. Now, let alpha dot v as 0 as u. So, it is u equal to u plus u. Now, u is an element in vector space. If u is an element in vector space, then additive inverse of u also exists, and it will belongs to v. So, we can take with add minus u both sides. Okay. Now, u plus its inverse is additive identity, and u plus inverse, u plus additive identity, so imply u equal to 0, and u is nothing but alpha dot u, which is equal to 0. So, we have proved the first part. Now, what is second? Second is 0 dot u. This 0 is from field, this is not additive identity. The things which I have marked by bold 0 is additive identity. Now, 0 is from field, then 0 dot with any u in v is always additive identity. Again, it is simple to prove. You can see it is 0 dot u is 0 for all u in v, then it is 0 plus 0 dot with u. You see 0 dot u can be written in this way. This is a real 0, and this 0 is 0 plus 0 is again 0. So, this is 0 dot u plus 0 dot u by the property of vector space. Now, if you take 0 dot u as v, then it is simply v equal to v plus v, and v is any element in vector space v. So, its additive inverse exists. So, we can always add its additive inverse both the sides, and it is 0, which is equal to v plus 0, and this implies v equal to 0, and v is nothing but 0 dot u equal to 0. So, we have shown that 0 dot with u is always 0. This is additive identity. Okay. The last property is minus 1, which is a real number, dot with u is nothing but additive inverse of u for all u in v. So, this is also simple to show. This is minus 1 dot with u is minus u, this is to show. So, let us write 0 dot u is 0, this we have proved in the second part. Now, this 0 can be written as 1 minus 1. Now, this 1 minus 1, because we know that alpha plus beta dot with u is alpha dot u plus beta dot u, because it is a vector space. So, this can be written as 1 plus minus 1 dot u equal to 0, alpha and beta. So, it is alpha dot u plus beta dot u equal to 0. 1 dot u is u, plus minus 1 dot u equal to 0, and if u is in V, then its additive inverse exists, which is minus u, and it is also in V. So, we can always add minus u both sides, and this plus this is additive identity. Now, element with its additive identity is always itself. So, it is minus 1 dot u, which is equals to minus u. So, we have proved this result also. Okay. So, all the three parts we have done. Now, this set of R plus, which is set of all positive real numbers, and we define the operation of addition and scalar multiplication like this, is also a real vector space. So, this is very easy to prove. You see that if you take now how addition is defined, addition is simply u into V, and alpha dot u is simply u times alpha, and for every u belongs to R plus, set of all positive real numbers, field is real. So, first we see with respect to addition. With respect to addition, it must constitute a abelian group. So, first is closure. You take let uv belongs to R plus, then u plus v, which is defined like uv, is also product of two real positive real number, is also a positive real number. So, it is also belongs to R plus. So, closure property is satisfied. Next is associative. If you take u plus v plus w, which is equals to u v plus w, it is now this plus will again multiply it and u v into w, which can be done as u v into w, because multiplication satisfy associative property, and this is u plus v w, and this is u plus v plus w. So, that means associative property hold with respect to addition. The second property hold, the first property is here. Then it is identity. You can take u plus 0, which is equal to u. So, u plus 0 is u into 0. This 0 is not a usual 0, this is additive identity. So, you can denote it by bar also or by any other number also. So, this is equal to u by this. So, this implies 0 bar is 1. So, here additive identity is 1. So, clearly the inverse of any element, if you take u plus v, should be additive identity. So, this implies u v equal to 1, and this implies v equal to 1 by u, which also belongs to R plus. So, identity, so inverse of any element is 1 by u, additive identity is 1 with respect to addition. It satisfies all the properties, of course, commutative also hold. If you take u plus v, it is u v, which is equal to v u, which is equal to v plus u for every u v in R plus. So, all the property with respect to addition is satisfied. So, with respect to plus, it is an abelian group. Now, if you say with respect to scalar multiplication, if you see for scalar multiplication, it is defined like this. So, of course, closure property holds. You take any alpha in real field and any u in R plus, then it raised to power alpha is always belong to R plus. That means closure respect to scalar multiplication holds. Now, you take 1 dot u, which is u raised to power 1, is u, satisfied. Now, you take alpha plus beta dot with u, which is u raised to power alpha plus beta, which is u raised to power alpha into u raised to power beta, which is alpha dot u. Okay. So, this is equal to, you see this dot is means addition, u alpha plus u beta, okay, because u plus v is u into v by that property, and this is alpha dot u plus beta dot vu by the definition of scalar multiplication. So, similarly, the next property can be shown that alpha dot u plus v is equals to alpha dot u plus alpha dot v. Okay. So, in this way we can show that it is a real vector space. Now, let us discuss few examples which are not vector spaces. You see, if you take V equal to R2 and over a real field and take any two arbitrary element A1, A2, B1, B2 in V, alpha belongs to field, and you defined addition like this, which is standard addition, and dot like this, then it will not constitute a vector space. The reason is very simple. You see, with respect to addition, it will be an abelian group, no problem. But if we see here, so for vector space 1 dot V should be V. If you take 1 dot A1 A2, it must be equal to A1 A2. However, it is equal to A1 comma 0, which is not equal to A1 A2, for A2 not equal to 0. So, this means all the property of vector space are not satisfied. So, it will not a vector space. If you take here, standard addition is the same, you see, no change in the addition operation. If you take the scalar multiplication like this, you take 1 dot A1 A2 is same as A1 A2, that is 1 dot V is V. But if you take the other property, say for this, if you take the other property, say alpha dot A1 A2 is alpha A1 and A2. If you take alpha plus beta dot with A1 A2, so it must be equals to, okay, comma, it must be equals to alpha plus beta dot with A1 and alpha plus beta with A2. You see, what I want to say basically, if it is a vector space, it must satisfy all the properties of vector space. If it is not satisfying any one of the property of vector space, means it is not a vector space. Okay. Now, if you take this property alpha plus beta dot with V, so it is alpha plus beta dot with A1 A2. By this property, it is, by this definition, it is alpha plus beta A1 and A2. Now, but for a vector space, it must be equals to alpha dot V plus beta dot V, which is alpha dot A1 A2 plus beta dot A1 A2, which is equal to alpha A1 comma A2 plus beta A1 comma A2, and which is equals to alpha plus beta A1 by the addition to A2, and this may not be equal to this if A2 is not equal to 0. So, for any A1 A2 this side is not equal to this side. So, this means it is not a vector space. Now, if you take R2 over a complex field, it will also not a vector space, because if you take scalars from a complex numbers and you multiply with the real numbers, the resultant is not in R2, resultant will be in C2. So, closure with respect to scalar multiplication is not satisfied. So, this means it will not be a vector space. Similarly, we can easily show that this addition scalar multiplication is same, standard one, but if you take vector addition, so vector addition is simply this thing, okay, and it does not satisfy associative property, you can easily verify. Now, if you take the real polynomials of degree greater than or equal to 2 over the real field, it is also not a vector space. You can see, if you take a polynomial, you take one polynomial of degree greater than or equal to 2 over a real field, you take one polynomial as suppose x square minus 1 and second polynomial as say minus or x cube minus 1 or minus cube minus 1, then u plus v is minus 2, which does not belongs to v, that is closure property with respect to addition is not satisfied. So, it will not constitute a vector space. So, in this lecture we have seen that what are vector spaces and what are the standard examples of vector spaces. In the next lecture we will see that what subspaces are and how we can find out basis and dimension of vector space. So, thank you.